start. So it's really a pleasure to have Biao with us. Unfortunately, not in person, but hopefully next time. So Biao is a very prolific physicist who just started as assistant professor in Princeton. And just as a very brief biography, so he got his bachelor's degree in Tsinghua in 2012. And already as a bachelor's student, he already had a few papers. So he had a paper by himself, actually, a very interesting paper on synthesis connections. Then he has a paper on astronomy, and he had a paper on cold atoms. And some continuation of that, so actually that was a series of papers. And then he moved to Stanford as a graduate student, working under the late Suchen Liang. Many of us knew. And there he really blossomed. He really worked on many different things, an amazing number of papers he wrote as a graduate student. And his main foci, I should say, were looking at anomalous quantum Hall effects, many different aspects of that, and topological, chiral-topological superconductors. And along the way, he expanded many facets of these fields, and also many other things that were not directly related to it at all. For instance, looking at what happens when you have orthodetection layered black phosphorus and transistors, and looking also, of course, associated with that, looking at axions in various situations, and looking at five-dimensional generalizations of valence metals. And the list goes on and on and on. And then he joined Princeton as a postdoc in 2017, and he was there from 2017 to 2020, again, doing an amazing number of works, all of which were actually, many of them are really very deep, looking at twisted bilayer graphene, something that he also pushed on thereafter. And I'm not going to go for all of it, I won't take too much of his time. And then, of course, they liked him so much that they kept him there. So since 2020, he's been the assistant professor at Princeton. And without further ado, I won't take too much of your time. Biao, it's all yours.
Thank you. Yes, thank you, Zohar. That's a very nice introduction, and it's really a great pleasure to virtually visit and talk about our recent works. Yeah. So I'll just start. So today I will be talking about some kind of combination between the topological states of matter and quantum dynamics. So basically, both topics have been one of the most focused topics these days in condensed matter. So I will be talking about the integrability and chaos of chiral edge states. And these chiral edge states are basically one type of the topological protected edge states known for topological matter. So this work is mostly based on our recent work. The earlier work is on a model we call chiral SYK model, related to the SYK physics. Some of you might know. Done at Princeton. And recently we've been generalizing the model to a model called chiral SY model, which I'll be talking about. And I'll be also mentioning a more physical system about fraction quantum Hall, which is in progress and will appear soon. Okay, so so the outline of my talk will be, so first I will be introducing chiral edge states in condensed matter physics, which appear as the topological edge states of topological states of matter. And when they have interactions, one could ask about the question whether they show integrable or chaotic behavior, just like the classical systems, classical mechanics. And that's what I'm going to talk about in the second part. So I will be particularly focusing on the chiral Majorana fermions. And in the third part, I will be talking about the other kinds of type of chiral edge states, which host the particles called Abelian anyons. And basically, anyons are kind of a generalization of the fermions and bosons in low spatial dimensions. Okay. So the concept of chiral fermion dates always back to Paul Dirac, who first discovered the equation describing electrons, or generic fermions in relativistic context. So basically, Dirac, of course, proposed the equation first in 3+1d, but this concept can actually apply in all kinds of space-time dimensions. For instance, in 1+1d Dirac equation is basically an equation like this with these matrices known to our physicists as Pauli matrices. But when Dirac proposed them, they are also called gamma matrices. And this is the mass of the particle. So basically, if this mass term is 0, then if you look at the energy spectrum as a function for momentum, the Dirac fermions in 1+1d just have two perfect linear dispersions with the slope being the speed of light. The particle can basically propagate either to the right or to the left. So then Hermann Weyl realized that if your mass is 0, actually this right moving, basically particles, fermions that moves to the right and fermions moving to the left, they would decouple. So he proposed this Weyl equation. Again, it can occur in many different dimensions, but in 1+1d, it's basically simply, you just understand it as the fermions. You just keep the right moving part of this fermion, and that's called a chiral fermion. So later, Majorana also realized another kind of generalization of Dirac fermions, which is the Majorana fermion. So basically, the concept is he assumed that there are some fermions that is charge neutral. And for charge neutral objects, basically, if this besides the annihilation operator of the fermion, he assumes that it's actually equivalent to the creation operator of the particle. So basically, annihilation and the creation of particle are kind of equivalent in this case, and that's just saying that your particle is equivalent to antiparticle. And again, in 1+1d, actually, you can propose both conditions that give you a Weyl-Majorana equation. Basically, it's a chiral-Majorana fermion. So here, by chiral, we just mean the particle moves only in one direction. But on the other hand, this particle, this Majorana fermion particle is equal to its own antiparticle. So what happens is basically these negative dispersions, which you can understand them as antiparticles, they're not independent degrees freedom. And for Majorana fermions, the physical dispersion are just this positive part. And if they're chiral, they're just moving in one direction. So this one dimension, these fermions that only moves in one direction is actually rare in nature, but surprisingly in condensed matter physics, they can actually be realized, physically realized on the edges of some two-dimensional materials. For example, so these materials are known as the earliest topological states of matter. So basically, if you have a thin film of topological matter and you consider its edge, there will be some electrons or some other kinds of states flowing on the edge, but only in one direction. And if you plot the dispersion, they will give you just the dispersion like the chiral fermions we just talked about, basically proposed by Weyl. And there are also other kinds of topological states which you can realize this chiral-Majorana fermion, which is basically a charge neutral fermion. The system that realizes these kind of fermions is for complex fermions. They are realized in the integer quantum Hall effect, which is basically some two-dimensional metal in strong magnetic fields, and the magnetic field turns out to allow only one direction motions of the electrons on the edge, and it gave you this kind of chiral fermion. And similarly, there are other types of states. One of the most known one is the chiral topological superconductor, which give you this actually charge neutral fermions on the edge moving in only one direction. So this is known as the chiral-Majorana fermion. And there are also the fractional quantum Hall states, which give you similar kind of chiral edge states. And actually, the fractional quantum Hall effects, unfortunately, I won't be able to explain it too much, but basically they allow even more kinds of chiral edge states. One big class of them are known as chiral bosons, basically are bosons that moves only in one direction. Okay, so just these chiral fermions actually lead to very interesting topological physics, but unfortunately I won't have time to explain them. Basically, but one of the most known effect is the integer quantum Hall effects. So if you have these chiral fermions moving only in one direction on the edge, and the bulk is an insulator, then if you do this, if you apply a current in the x direction, there will be a voltage, Hall voltage, generated in y direction, with a coefficient known as the Hall resistance, quantized in units of the h bar and e squared, basically the electron charge. And this n here is the number of chiral electron edge modes you have. For this example, I just plot 1, so this is n equal to 1 case. And similarly, if you have a chiral Majorana fermion or all the other kinds of chiral edge states, they also give you a chiral, thermal Hall conductance. So thermal Hall conductance is basically when you apply a temperature gradient in one direction, you would get a heat current in the perpendicular direction, and the coefficient is again quantized in units of degree of freedom on the edge, which are called chiral central charges. You can basically roughly think of them as equal to this n here, but in this case, it doesn't matter whether the particle carry an electron charge. Okay, since I'm going to talk about integrability and the chaos, just some brief introduction about these concepts in classical mechanics. So integrable systems are just generically known as systems that you can predict their evolution accurately with some initial conditions. Basically, that means the evolution of the system is insensitive to perturbation, small perturbations. For example, the pendulum system is an integral example where we know in phase space their orbits are just periodic and insensitive to small changes of initial condition. In contrast, the chaotic system are kind of systems which are pretty sensitive to initial conditions, and this is known as the butterfly effect. Basically, if you perturb the initial state a little bit, you can go to entirely different states. So both of these concepts generalize to quantum systems. So for quantum systems, if a system is quantumly integrable, what happens is the quantum states, basically it's some quantum waves of the particles would remain coherent. Just consider some, for example, the simplest case being some free particles. So they would usually be quantum coherent and give you coherent interference, etc. Such behaviors. While for quantum systems that show chaotic systems, chaotic behaviors, what happens is the quantum coherence would easily be lost. And actually, the quantum chaos has been believed that to be closely related to the decoherence and thermalization of a quantum system. Basically, that's how you get into the same temperature starting from some temperature gradient. Okay. Yeah, so generically, most systems are chaotic, but the chiral edge states are probably one of the very few examples in condensed matter physics or in materials that could be highly coherent. And people have actually been using the fact that they are coherent to design some interference experiments. Yes, so basically, for example, this is a recent experiment actually used to determine the braiding statistics between anions, which I won't talk about too much. But the basic idea is this is a topological state of the integer of the fractional quantum Hall state, actually known as the Laughlin 1/3 state, and there will be chiral edge states flowing on the edge, and these two edges, the particles flowing on these two edges can actually interfere through different passes, through this pass or through this pass, and because the edge states are highly coherent, they can actually see a well-coherent pattern, interference pattern of these edge particles. And similarly, this is experiments which you can sort of think of it as the interference of chiral Majorana fermions. These are produced by attaching a superconductor to the material, which produces the chiral Majorana fermions. And again, the data is not perfect here, but you see these oscillation patterns due to the interference. So mathematically, this would mean that quantumly, the surviving coherent has to be due to some integrable structure of the quantum model in this case at low temperatures. And indeed, this is the case in actually several examples, including the example I just presented. So yeah, if we were to try to understand why these chiral edge states are often integrable or often quantum coherent. So one example is we can consider just the chiral Majorana modes, but now multiple of them flowing on certain edge. So the idea is, so this is the kinetic energy. Of course, each mode would have a kinetic energy with the Lagrangian like this. This just gives nothing but the chiral Majorana equation for these, that governs this motion of these Majorana fermions, making them moving only in one direction. But you can try to write down what interactions these fermions have. And the interactions are generically believed to give you some collisions and lead to decoherence finally. But if you just consider n smaller than or equal to 3 flavors of Majorana fermions, you would find all kinds of interactions are just irrelevant in the so-called renormalization group sense. Here, irrelevant just means these interactions are unimportant at low temperatures. You can basically ignore them in theoretical treatment of their quantum model. So as a result, basically these chiral Majorana fermions would behave as free particles, basically collisionless particles at low energy. That's why they remain coherent. And similarly, I won't explain too much, but if you look at the 1/3 Lyapunov fraction quantum Hall edge state, so they're actually described by a chiral boson theory. You can also try to write down all the interactions available in the system, and they would always be irrelevant. Okay, so the first non-trivial example is if we consider 4 flavors of chiral Majorana modes. But in this case, it's actually a very classical example of interacting quantum model in condensed matter. That's, in this case, the interaction between the fermions doesn't destroy your coherence. It's still an integral model, which is known as the chiral Luttinger liquid model. So the basic idea is, so yeah, I should mention that actually 2 flavors of chiral Majorana fermions are equivalent to 1 flavors of complex fermions. Okay, so in terms of Majorana fermions, if you have 4 flavors of them, you can write down a leading interaction, which has to be a 4 fermion interaction. So at least you would need 4 flavors of Majorana fermions to do so. Then there's just the 1 interaction in this case. It can be rewritten into a more familiar form if you define these complex fermions, complex chiral, basically complex Weyl fermions, as the linear combination of the psi1, psi2, and psi3, and psi4. Basically, in some sense, the Majorana fermions behave as real numbers, and the C, in this case, would be kind of a fermionic complex numbers. So this could be thought of as a spin up electron and a spin down electron. Then you can rewrite this model as just a chiral fermion with the interaction between the spin up, with a just Coulomb interaction, kind of a local repulsive interaction between spin up and spin down fermions. And this model is known to be exactly solvable at quantum level, and it will give you a integrable behavior with the so-called spin charge separation phenomena. Yeah, just to give you some more details. So the basic ideas, basic technique for solving such a model is known as the bosonization technique. So the idea is for this fermion operator, I can take its phase, the phase of this complex fermion out. Basically, this fermion is some complex fermionic number. But in this way, I can define a boson field basically as its phase. And it's surprisingly actually, as first shown by Houdan in continuum models and also Mattis and Lieb in some discrete version of this model, you can actually map this problem into a boson problem. Basically, basically you define the boson field in this way, then you find this interaction term becomes a term just quadratically in the boson fields. Yeah, basically these bosons are just like the Klein-Gordon boson fields, but now they are just moving in one direction, and it's guaranteed by this action here. So then this action actually becomes a free boson action that allows you to easily solve for the spectrum. And there are actually two species of bosons that actually gave you two eigenboson modes with different velocities. Okay, so here the velocities, you can think of them as just the speed of light, but in condensed matter it's given by some the system as some Fermi velocity and the interaction parameters. And these two boson modes, if you look at the charge density associated with these two boson modes, the one with the slower velocity actually correspond to opposite charge density in spin up and spin down electrons. So that's actually a spin fluctuation, while the fast mode give you the same sign of the charge density in spin up and spin down. So the physical meaning of these two bosons are basically telling you that the spin degree of freedom and charge degree of freedom of this electron here, this fermion here, will propagate at different velocities. But because they are free bosons, the coherence are actually maintained. And you can actually map it back to fermion picture to calculate the Green's function of the fermion propagator, the electron propagator. And in this case, it actually gains contribution from both velocities, both boson velocities. And so if you look at the spectral weight of this Green's function, it's basically imaginary part of the retarded Green's function. It kind of tells you the density of states of this electron in the system. You see it's bounded between the two velocities, basically. And this is one experiment which is actually done in a non-chiral, basically non-chiral nanowire, but the chiral part, the unidirectional part of the physics is the same. And they indeed see basically two different velocities in the Green's function, or the spectral weights of the fermions. Okay, so now let me keep talking about more generically what happens for chiral Majorana fermions. So we asked the question, so is the, if you just turn on the four fermion interactions among different chiral Majorana modes, is the integrability always preserved or not, or it's going to break down at some point? So here we consider Majorana fermions because basically complex fermions or charged fermions are just you can think of them as linear combinations of the Majorana modes. So generically, if I have n identical, just n flavors of identical chiral Majorana modes, then I can add just more four fermion interactions among them. Basically, as you can see, if I have n flavors of Majorana fermions, the number of interactions here would increase quickly, actually, as function of number of flavors of Majorana modes here, and so they finally grow in proportional to n to the fourth. So basically, this model you can think of it as you have n copies, you stack n copies of chiral. For example, chiral topological superconductor at the same position, so their edge states would just interact among each other. And generically, if I don't have any symmetries, then the interactions could be random between them. So the interesting thing about this is this term. This term is always in the terminology of renormalization group. It's actually exactly marginal term. Basically, this means this term is the same important as this kinetic energy at all energy scales. Basically, at all temperatures, this term is important. And you can see, as you can see in the earlier n⁴ case, this J just modifies your speed of light, or basically your velocity. So that modification is important at all energy scales. So so basically you ask the question, is this model still solvable when n is greater than 4? So we know that n equal to 4 is basically the chiral Luttinger liquid theory. So it turns out that if we go to n equal to 5 and n equal to 6 flavors of Majorana fermions, they are still integrable, and they still give you the free boson theory. The idea is, although you have many interactions in this case, you can basically simplify the problem by choosing a proper fermion basis, Majorana fermion basis, and then do the bosonization procedure. So for n equal to 5 case, actually by rotating this, basically it's because the kinetic energy actually have a SON rotation symmetry among all the flavors. Basically, all the flavors are identical. You can always choose a proper basis to reduce the number of interactions, four fermion interactions, from 5 to just 1. And as a result, in this new fermion basis, you just get one interaction among the first 4 flavors, and the 5th flavor just decouples. So basically, the n equal to 5 model is just equivalent to two free bosons plus 1 free chiral Majorana fermion. So it's still an integrable model. So for n equal to 6, the story is similar. But now you have 15 interactions, and by choosing a proper basis, you can actually reduce it to just 3 interactions. And after bosonization, they give you just a free boson theory. But in this case, it's not. The coefficient is kind of more random. They don't correspond exactly to spin and charge modes, but they correspond to different combinations of the 3 flavors, 3 fermion, boson flavors of the model. But things become interesting when you reach n equal to 7. So now you're in the number of interactions is actually increasing very quickly to 35 or more. And in this case, you find no matter how you, what fermion basis you choose, you cannot reduce it into a free boson theory after the bosonization procedure. So basically the idea, so here I won't talk about the details, but if you somehow change some of these fermions, map them into e to the I phi, as that's basically the procedure of bosonization, they would end up with many cosine and sine terms after you've done with the mapping. So if you do bosonization, you actually get a nonlinear theory, nonlinear equation motion for bosons. So basically in this case, either in fermion case or in the boson case, you get nonlinear equations motions. And once things become nonlinear, we know that in classical physics, many things become chaotic. So that's actually what we conjecture here. So that's your system actually become quantum chaotic when the number of flavors of Majorana fermions increase to greater than 7 or equal to 7. And accordingly, this would have an effect on, for example, the coherence and thermalization of these edge states. So imagine these states are living on the edge of some topological phase. Then you would expect below 6, you can still have some quantum coherence and design coherence interference experiments. But for large flavors, you would expect basically these modes would thermalize into the same temperature without coherence quickly. For example, if they start from different temperature sources, then they would thermalize just quickly. Okay, so the generic model actually is quite difficult to solve if you consider generic n. But with physics, for physicists, it's always easy to do either small n, like 2-body problems, 3-body problems, then, or you go to large n and have an infinite number of particles. So that simplify your problem again. So again, so similar for this model, a solvable point is actually when you go to large n limits, if you have many flavors of chiral Majorana fermions. And this model actually, we define it as a chiral Sachs-Diffie Kdaf model, basically because of the similarity to a solvable quantum chaotic model known as the SYK model. Yeah, so basically in the large N limits, what we assume is these interactions are fully random. Yeah, so again, so these coupling constants, they are uniform in space and time. So the randomness is just with respect to the flavor index. And we assume they are randomly randomly generated. So yeah, they don't have any correlations between different couplings. But J squared, so J squared of each coupling constant has a average expectation value like this, with this coupling strength J defined here. And this n to the third actually is necessary because you don't want your energy to diverge, and this n to the third gives you the correct scaling to make sure your energy, the energy of this model doesn't diverge. Yeah, so basically this is similar to the actually pretty extensively studied model in 0 dimension known as the SYK model, which is solvable quantum chaotic model with many interesting physics, including duality to a black hole and relation to some spin glass physics. So the basic idea here is in the 0 dimension case, it's basically a model with just the interact with a bunch of Majorana modes, Majorana fermions in 0 dimension, but a random Q fermion interaction among all of them. So here in our case, this Q is fixed to 4, and that's actually the physical case. So physically in nature, we only have the important interaction is 4 fermion interactions. So in that sense, this model is kind of a minimal generalization of this model into 1 dimension, and you just keep the chiral degree of freedom. And here in our model, a difference is actually this model is scaling invariant. As I said, this term is actually exactly marginal. It's important at all temperatures. This is different from the SYK model. Actually, this model would dominate over this term at low energies. That's slightly different physics. Okay, and again, there's no Lorentz symmetry in our model. Yeah, basically, like in the n equal to 4 case, we end up with 2 speed lies, and that breaks the Lorentz symmetry if you think of it as a high energy like model. But that's actually natural. In condensed matter, we don't actually have the Lorentz symmetry. Okay, so the large N limit basically allows you to throw away many terms when you do calculations, for example, the Green's function of the fermions. Yeah, basically, I won't talk about the details, but if you just keep the leading one of the n-order Feynman diagrams, contributing to the fermion Green's function propagator, it turns out to give you a solvable differential equation that you can use to get the solution. And so basically, if I define a Green's function of the fermions as I generate a fermion at 0, 0, a Majorana fermion at 0, 0, and measure it at time tau and position x. So this tau here is actually imaginary time, but yeah, Euclidean time. Then I can obtain the solution. Yeah, here is in real time again. So if you look at the solution, it's actually given by this very nice formula, and with the two velocities related to the coupling strength, the random coupling strength of from the 4 fermion interactions by this formula. So here we require this coupling J to be smaller than 2 pi to keep all the velocities positive. Yeah, basically this is a kind of physical requirements for a model, yeah, for a model to be really a chiral state of the condensed matter system, because everything has to move at positive velocities to the right. Okay. Yeah. So so if you remember our earlier results from the chiral Luttinger liquid for n equal to 4, this Green's function actually looks exactly the same as the n equal to 4 case, which is actually surprising, kind of a which I haven't actually fully understand, because their physics are actually pretty different. But it just happens they're 2-point functions, Green's functions, the fermion propagation function are the same. However, in this large n case, it's unlike the n to the 4 case, there's no quasi-particle. While in the n to the 4 case, actually, you do have quasi-particles as free bosons in your system. Yeah, to see there's no quasi-particle, basically, the idea is to look at quantum chaos, which I'll talk in next slide. But before that, I just briefly mentioned that we can actually use the finite temperature solution to obtain some thermal quantities. So again, so the first quantity one can calculate is this: if I have apply a temperature gradient in one direction, I generate a thermal currents in the y direction, and I can look at the Hall conductance, the thermal Hall conductance of the thermal currents, and that's still quantized in the correct units. So this is kind of expected because this is actually known as the topological response, which should be quantized independent of changes of the details. But this is still interesting. Basically, it says interaction doesn't affect the quantized thermal Hall conductance, but it does affect the thermal entropy density if you calculate that. So basically, these U plus U and EU minus are functions of the interaction strength, so it affects your thermal entropy density. For those who are familiar with the original SYK model, so the original SYK model actually tells you there is a zero temperature entropy that is extensively large, proportional to the number of flavors of fermions. So that's indicating the zero temperature, the zero dimensional SYK model is actually a spin glass. But in our case, actually, the zero temperature entropy density is still 0. And that's actually easy to understand because we showed actually the spectrum is lower bounded by this velocity here. So there's actually no, if you look at any finite momentum, there's no quantum states near 0 energy. And at 0 temperature, basically you don't have that many of microscopic states to give you the extensive entropy. So to understand the chaos in this model, which is indeed the case, we need to introduce another concept which originates from the classical mechanics, known as the Lyapunov exponent. So basically, for a classical system, this is basically the butterfly effect. If you perturb the initial state, for example, in the phase space to a slightly different position, then the evolution of the two states would, the difference between them would grow exponentially, actually, in this form. And this is basically giving you very distinct final states and give you quantum chaos, give you classical chaos, in this case, still classical. And the distance between these two states in phase space are actually growing exponentially with this lambda here, known as the Lyapunov exponent. Okay, so quantumly, there's also corresponding quantity that people propose to diagonalize this exponential growing behavior, which is known as the out-of-time ordered correlator. So basically, the classical analog would be if you consider some this acts as some distance between the two initial states, then you want to examine the change. Basically how much the final state at xt at time t would change with respect to the initial condition. Then the quantity you would look at is this partial x, partial t. And quantumly, basically I do a squared because quantumly it could give you some average. So you don't want your average to be 0. You make a squared of it. So classically, this should grow exponentially in time. And quantumly, you can just convert this. This is actually a Poisson bracket, and you can convert it into just a commutator between the momentum and x operator. And if you expand it, this is actually some 4-point function, 4-point correlation functions, as shown here. In particular, this term actually, you go from time t equals 0 to time t and to 0 and t to t again. This is known as the out-of-time ordered correlator. And people have kind of proved that the exponential growing behavior can only come from this piece, while these terms, they would not give you the exponential growing behavior. And so quantumly, actually, there's a result that shows that this quantum exponent from this out of time autocorrelator has an upper bound at temperature T, kBt. So this upper bound is 2 pi kBt over h bar. So in the classical limit, this bound vanishes because h bar goes to 0. Okay, so for the large the Chiral SYK model, basically we can calculate the out of time autocorrelator for the fermion operators. This is not exactly corresponding to the P and X operators I talked about earlier, but it's also giving you the exponential growing behavior if there's quantum chaos. Yeah, basically it's generating a fermion at 0 and detecting it at time t and position x. So the OTOC of this correlator generically behave like this, and like a function like this. It has a order 1 piece, which is roughly constant. Then there's a exponential growing behavior, which is to the leading 1 over n order. But as you can see, as your time approach the beta log n, beta is the 1 over the temperature, then this term grows to order 1. And this approximation is no longer, this approximation is no longer valid. So basically, what this function, the behavior of this function is within this time scale, it behaves as an exponentially growing function plus a constant piece. And it's this exponent that we can define it as the Lyapunov exponent. And here in this model, because it's a 1+1d model, you can actually look at the exponential growing behavior along a fixed velocity. If I just choose my x to be equal to vt, as shown here, then I can look at the growing behavior as function of time t, as well as function of velocity v. And so I won't show the calculations, but this is what we find. So basically, all the informations are bounded by these two velocities, which I mentioned earlier, u minus and u minus, which appear in the retarded Green's function of the fermions. And actually, they define the causality cone. So basically, outside these two velocities, the fermions cannot propagate. Basically, the retarded Green's function is 0. But within this causality cone, you find all the Lyapunov exponents are positive. So that's basically saying all the information propagating within the causality cone of this model are chaotic. And this, if you look at the largest velocity-dependent Lyapunov exponents within the cone, it's actually a function of the coupling strength J. And this function, this Lyapunov exponent approaches the maximal chaos bound in quantum models when your coupling strength goes to 2 pi. And this is actually the largest allowed interaction strength, which preserves the chirality of the system. Basically, when J is 2 pi, this lower bound of velocity goes to 0. And if you go beyond that, actually you would start to lose chirality. You would have some anti-propagating modes, which is more complicated, which I won't talk about today. But in comparison, if you look at the OTOC of the integral model, for example, the n equal to 4 case, it only shows exponential decaying behavior. Actually, if you write down the analytical expression, you will see this is only contains exponential decaying behavior. Okay, so that's for large n. But earlier we conjectured that the transition of integrable and chaotic actually happens when the number of flavors n is at 7. So in order to look at that, we actually did some numerical study because the analytical study is pretty difficult. So one thing that could be used to probe chaos in quantum system is known as the level spacing statistics. So the idea is if you list the energy levels of a quantum model and look at the spacing between nearest neighbor, between the nearest energy levels, So this quantity, this energy difference would satisfy a certain distribution. And they actually tell you whether the system is chaotic or integrable. So it was first discussed by, actually first by Wigner and Dyson for random matrix models. But later in many body systems, generalized to generic models by Bohias, Glanoy, and Schmidt, that they propose that if you have a quantum chaotic system, then this distribution of the level spacing would follow a distribution known as the Wigner-Dyson distribution, which is calculated for the random matrix Hamiltonians actually. So the function just look like this, and this is an example of a nuclear, nuclei energy levels, which is you can understand as a zero-dimensional quantum chaotic system, and it does fit this curve pretty well. Instead, if your system is integrable, this distribution would satisfy the so-called Poisson distribution, which is for random independent variables. And so it's basically exponential decaying function. And this is what we found from exact diagonalization numerical calculation. And for n equals 7, we find basically, we look at a fixed total momentum sector of the eigenstates. And indeed, it shows a perfect Wigner-Dyson distribution. So that actually confirms our conjecture here that when you go to n equals 7, your system becomes quantum chaotic. This is still in progress, but if you go to n equals 6, your energy, basically the level spacing actually becomes almost a delta function. It's not even well-defined Poisson. You can think of it as a Poisson distribution with an infinitely large exponent. But the delta function structure here is basically because there's lots of degenerate levels due to the free nature of this model. Actually, because it's a free boson model. Okay, so this is about the Chiral-Majorana fermions. So in the remaining time, I want to briefly mention basically these studies can be generalized to more chiral edge theories, which can arise on the other the edge of the other topological phases. So one example we generalize is to generalize the model to kind of a model which hosts the Abelian anion particles. Basically, anions are kind of particles which we know like as generalizations of fermions and bosons. So for fermions and bosons, if you exchange two particles, you get a pi and 0 phase respectively. But in low dimensions, in 1 dimension, 2 dimensions, actually, when you exchange two particles, the phase change of your wave function doesn't necessarily be 0 and pi. And for generic phases, these are known as the anions. So basically, we want to find a model which hosts the anions, which actually occurs quite often in fractional quantum Hall edge theories and bulk theories, but at the same time exhibit quantum chaos. So the model we look at is this so-called Weissman-Witten model, which I won't have time to explain in details, unfortunately. Basically what happens is the model actually have some chiral boson description, but at the same time we introduce a current interaction among these different copies of Weissman-Witten models. So each of the model can be thought of as an edge theory of certain bosonic fractional quantum Hall state or a chiral spin liquid state. And these current operators are actually, you can think of them as one-dimensional generalizations of the zero-dimensional spins. Basically they satisfy the commutation relation in 1 dimension, but you see here these are basically the group structure of SUMs. So basically these operators, you can think of them as 1-dimensional generalization of SUM spins. So that's why the name, we call it Chiral SY model, basically because the first quantum chaotic model actually studied by such and it's a 0-dimensional spin model of SUM spins. So this is just the generalization. And this model, but the nice thing about this 1D model is they host the anion excitations that give you this non-zero non-pi braiding phase. Okay, so I just mentioned that this model actually have both integrable and chaotic cases. So if you just assume all the interactions are uniform between different copies, so then the model actually is an integral model. It actually factorizes into two pieces which are known as different conformal field theories. Yeah, the mathematical structure of which are pretty well studied. But the thing is, this interaction J actually split the speed of light of these two conformal field series. So basically, each piece can be thought of as a kind of a high energy model of conformal field theory with its own speed of light. Okay. So an example is the n equal to 2 and m equal to 2 case. Actually, yeah, so I should mention, so m here is the spin. Basically, if you consider just the SU2 spin, which is the Euro spin we consider, and you just have two copies, then this model just describes two interacting edges of the filling 1/2 bosonic fractional quantum Hall state. And as a result, what happens is the edge theory, interacting edge theory is equivalent to three chiral Majorana modes at this velocity and one chiral Majorana mode at this velocity. And you can look at the anion Green's function for basically in this model, it actually gains contribution from both velocities. Okay, so in the large N and M limit, it's interesting actually the model by some mapping of enlarging the Hilbert space, you can map it to a fermion model, which is known as the complex version of the Chiral SYK model we just studied. And this allows us actually to calculate everything in terms of fermion variables. And in particular, the anion operator, is actually related to the fermion operator by this relation, where this phi prime is actually some fields we introduced, ancillary fields we introduced to enlarge the Hilbert space. And as a result, you can calculate actually the 2-point function as well as the OTOC of the anions, which actually just gains another factor which governs the anion statistics of the particle. But there's also a piece which is the same as the Chiral SYK physics I talked about earlier, which gave you the same chaos exponent, actually. Okay, so now let me talk about another example, which is more realistic. So in the earlier models, we all need at least some kind of large enough number of chiral modes to get quantum chaos. That's also why kind of the chiral S states in experiments are kind of robust, because we usually don't have that many flavors. So so we want to consider some systems, some small degree freedom system. And the interesting example we consider here is the filling 4/3 fractional quantum Hall state, the edge theory of this state. So basically the theory can be understood as a 1/3 Laughlin fractional quantum Hall state plus integer quantum Hall state. And this 1/3 Laughlin states, unfortunately I won't have time to explain it, but basically it gave you some anion fractionalization of the electrons. So basically each electron on the edge of this 1/3 Laughlin state fractionalizes into three charge E/3 anions, which give you a fractional non-zero non-pi braiding statistics. Okay, so then on the edge actually you have two kinds of excitations. So one is charge E/3 anion and one is charge E anion electrons from the integer quantum Hall part. And these two can be used to define two boson fields, phi 1 and phi 2. And that actually allow you to write down a chiral Luttinger liquid theory, which is usually how people describe the edge of such systems. But actually you can, for the first state, the interesting point is you can also write down a scattering term for an electron in the 1/3 Laughlin state to the integer quantum Hall state. So basically you need 3, and the factor 3 here, because you need to create a charge E object and scatter it to the other copy. And this term, if you look at the scaling dimension of it, it's also a marginal interaction, exactly marginal interaction. So that means it's going to affect your low energy physics. It's important at all energy scales. And interestingly, if you recombine these boson fields and do a refermionization, you can map this theory into an interesting fermionic model. But now this fermion actually is pretty weird. It carries a irrational charge, electron charge, but the other fermions are charge neutral. So the resulting model is just the 2 chiral complex fermions with the interaction. So this is the same, similar to the n=4 chiral Luttinger liquid theory. But again, for this neutral fermion, it actually has a superconducting pairing term, which creates or annihilates two fermions at the same time. And so this model has 2 solvable points. So the first point is when J is 0, basically when the scattering term is absent, then you don't have this pairing term. Then this is nothing but the basically like the chiral Luttinger liquid theory, where you can think of Cn and C rho as the spin up and spin down fermions. So they give you they bosonize into 2 free bosons with different velocities. And as a result, you can calculate all the correlation functions either in the n and the rho fermion basis, or you can go back to the anion basis to calculate the anion propagators. Which you can see actually acquires contributions from the 2 free boson velocities. Well, the other point is when this velocity matrix happen to be satisfy V and rho is 0, basically when n and rho don't have an interaction between each other. So this is generically determined by the Coulomb, the local interaction on the edge. If we tune it to this point, then we find this model actually is just free fermion model. So the behavior should be just look like free fermions. You have these free fermion propagators in the n and the rho basis, but this pairing term actually splits the complex fermion Cn into two chiral Majorana modes with different velocities. So as a result, in this case, you have 3 fermion velocities in the system. Actually, 2 of them are Majorana, the other is complex. And as a result, if you now look at the anion correlation, you would get contribution from 3 different velocities. Yeah, so these two points are kind of interesting because one is free boson and you get 2 velocities, and the other is free fermion and you get contribution from 3 velocities. So what about in between? Basically, that's the interesting we are looking at in progress still. Yeah, so basically, if you look at in between, then the behavior you would expect it's between free fermions and free bosons. But what we can do is now is again to do an exact diagonalization study. The analytical study again is unfortunately difficult. So the interesting thing we find is if you look at this generic J not equal to 0 and V and rho not equal to 0 case, if you look at a fixed sector with all the conserved charges, in this case, the charge of rho fermion, for example, is conserved, then you see a Poisson distribution. So this indicates the model might not be quantum chaotic. So it's possible that it's still an integrable model based on the level spacing statistics criteria. Of course, there's also a possibility that there are just hidden conserved charges that I haven't found yet, but it's actually still quantum chaotic in the sector you finally look at. That's also an interesting question. What's the hidden conserved quantities here? Yeah, lastly, just let me briefly mention that this is the spectral weight of the 3 cases you can see. Actually, this case is the free boson case. It actually agrees with your boson solutions. This is a free fermion case. You have 3 different velocities, and you can see kind of the spectral weight start to dissolve into 2 velocities in between when you're having both parameters non-zero. And so one usual question would be, what would the interference of the edge state of fourth third state be affected when you have both terms non-zero in general? Okay, so with this, let me conclude my talk. Yeah, basically I talked about the Majorana fermion model, which I showed there's a transition from the conventional Luttinger liquid behavior to chaotic when your number of flavors, fermion flavors increase to some value here, it's 7. And you can actually generalize the model into some other more fancy chiral edge theories, which hosts anions. And for the fourth third fractional quantum Hall state, which is a simpler example, it seems to behave the oppositely. So basically, it's still possible it's an integrable model instead of quantum chaotic. And it will be interesting to look at the interference of these edge states. With that, I'll conclude my talk and thank all my collaborators. And yeah, questions are welcome. Thanks.
Well, thank you very much, Biao. Thank you for a great colloquium. I mean, so are there any questions that anybody wants to ask?
I have a question.
Yeah.
So yeah, this is really interesting. I'm wondering if you have some irrationally charged degrees of freedom at the edge. Does that have any consequences in the bulk? I mean, you couldn't have irrationally charged quasi-particles in the bulk, I believe, but maybe I'm wrong.
Right, yeah, that's a very interesting question. Basically, you were saying if you go to the free fermion limit, for example, I tune the system to this point, how do I understand this fermion? Yeah, so actually, as you can see, like the transformation into this fermion involves the irrational coefficients. That's how you get this irrational charge. That's in principle not quite allowed when we usually do transformations. If you consider carefully about zero modes on the edge series, so I suppose the bulk physics would be similar to the zero modes. So that's why you're generically not allowed to have these irrational charges. But if you have some open edge these systems, that's actually very interesting. I don't know how people could detect the charge of these objects, but maybe, of course, the physical object you can inject is still electrons, right? So then it will actually, according to this case, I didn't show the charge E correlation actually, but if suppose you inject the anion into it, it's also similar. Then it would fractionalize into these 3 different velocities. Then if you just measure maybe one branch of it, so I don't know if you could measure these charges. Actually that's interesting, because in the bulk people indeed measure like E/3 charges for the 1/3 fractional quantum Hall state, right? Yeah.
Intriguing. Well, thank you.
Yeah, thank you for the question.
Are there any other questions? Okay, maybe ask. Oh, sorry, Lucas. Sorry, you had any question? Sorry.
Yeah, hi Biao. So I have a question regarding the chiral SYK case in the large n limit. So there you said that when J goes to 2 pi and the velocity u minus goes to 0, the Lyapunov exponent reaches its maximal bound.
Yeah.
Now, is it correct to somewhat deduce this from the maximal Lyapunov exponent from the 0+1d SYK model? Because I'm thinking that if the velocity goes to 0, it effectively becomes a 0+1d SYK model.
Yeah, very, very good question. Thanks. So so basically there's some similarities, but I would say it's still different from exactly zero dimension, because we know like in 0 dimension the interactions are relevant instead of marginal. And here if your system is infinite size, then you always have marginal, basically temperature independent physics. But in some sense, when this velocity u minus reach 0, indeed, this maximal Lyapunov exponent is reached when you consider zero velocity. Yeah, basically, the Lyapunov exponent is a function of velocity, so it's indeed maximal in this direction. So in that sense, it looks like these fermions are kind of static, staying in its own position and give you the maximal chaos. Yeah, but the interesting here is no matter which temperature you go to, it's always maximal chaotic. While in the zero dimension case, when you go to high temperature, it's actually deviate from the SYK physics.
Yeah, that's true.
Mm-hmm.
Okay, yeah, I mean the analytical is just very much daunting, but of course there should still be some things that are different. Yeah, thanks.
Yeah, sure.
Actually, maybe ask a silly question. I mean, so for instance, so can you do, say, 1/n expansion about the infinite n limited for SYK-like physics?
You mean why it's SYK looks like?
No. So you discuss, for instance, the small n, and you saw a transition between 6 and 7. And then you looked at the infinite n in the SYK-like physics. So,
right.
And you show the diagrams that you have for it. So could you do a 1/n expansion, for instance, about the infinite n case and sort of see corrections to SYK-like physics?
Yeah. In principle, you can do that, but maybe not to too many orders. You can go to next order. That would be what people call the Schwarzian corrections. But actually, it might be different here. That's also an interesting question because if you're familiar with the Schwinger-Dyson equation of the SYK model, unfortunately, I didn't have it here. So that's people say there is a conformal symmetry of that Schwinger-Dyson equation, which actually allows you to. That's why the Schwarzian correction actually arises. Here actually because you can't ignore this term. So in zero dimension, the point is you can ignore this term, then you have a higher symmetry. You have a full conformal symmetry, and that gives you the solution. But here you can't ignore this term. This term is actually important when you solve the question. But the solution somehow looks like you still have some conformal symmetry, because the finite temperature solution is actually related to zero temperature solution by a kind of weird conformal transformation along these two velocities separately. So yeah, we haven't done that calculation, but it seems much harder in 1+1d, but you might still get some Schwarzian correction. That's my guess if you go to 1/n order. Yeah, but if you want to fit that with n equal to 7, probably it's n equal to 7 is still too small. Yeah. So at least numerically, if you try to look at for example, the OTOC numerically, you barely see the exponential growing behavior in n equal to 7 or 8 because this window is too small. When log 7 is too small, basically. Yeah.
Thank you. Actually, are we other questions? Actually, I had never sort of silly question. I mean, a few questions. So first of all, I mean, basically a comment that Alex made. I mean, and you emphasize sort of so the rational statistics that you actually have. I mean, rational charge, which would suggest also that you have rational angular momentum. I mean, basically, if you're doing a Renaud-Baum type effect, as you could, for instance, if you imagine looking at the Renaud-Baum type phase, you can think about it in terms of charge, the absolute compass. I mean, the flux that you have, but of course, if you go around with the charge flux, or equivalently, you can make it basically a rotation about the center of mass, which is essentially the total angular momentum that you actually would have. And the two have to be the same, so that would imply that the angular momentum would also, if you can perform this exchange, of course, in the bulk, if it was in bulk, then it would be imply rational momentum.
I see.
Suggest rational momentum.
Yeah. So actually, that's a very interesting question. But basically, if you, for that, I guess you're considering a closed
exactly
boundary condition,
if you
right?
can, if you can. That's a caveat, exactly.
Yeah. So my guess is you still get quantized. Yes, the correct integer angular momentum,
Yeah.
because we said that this transformation is actually illegal if you want to consider zero mode things, which I think is kind of finally relates to angular momentum of the edge states. If you consider closed boundary, yeah, basically this is problematic because phi 1, for example, phi 1 and phi 2, they are defined modulo 2 pi in general, right? But if you consider closed boundary, when you go back, suppose phi 1 increased by 2 pi, then this phi rho would increase by some irrational phase, which is problematic. So I would think if you have a closed boundary, you might end up with maybe just some rational number closest to this irrational.
Exactly.
Yeah.
Exactly.
Mm-hmm.
But actually, another silly question on my part. I mean, and this is people. I mean, everybody sort of says this, and everybody uses it. I just don't know the answer why it's like this. So I have to apologize. So this lower with Poisson statistics are integrable, and when it's the Dyson triangle, like it's not. I mean, is there some sort of theorem behind it, or some intuition behind it? Why is it? So as you point out in your case, also with the fact that you have Poisson suggests that maybe it's actually integrable. It's not obvious how, and so on. In the last case, I mean, is there sort of intuition why that's the case in general?
No, I don't have such intuition so far. Yeah, so I guess the only intuition I have is like in the Chiral YK model I mentioned. If a number of interactions increase to many interactions, like as you increase the number of flavors, then of course it's the chance of solving it exactly is going down directly. Basically, I guess the point is we don't yet have a good definition of integrability, even in quantum sense. We only know it's integrable if we can solve it. But there's some indications, but we don't know. There's no strict definition of it. So I don't really know why in this case it's integrable.
No, you just I always find it interesting. People always make this connection. I just would like to know, I mean, why something deep behind it.
Yeah, I also hope to get some deeper understanding of this, maybe by trying to solve this model analytically in the future.
So are there any other questions that anybody else has? Okay, I guess in that case, thank you very much, Biao. I guess for you it's even later. So really, thank you very much. It was very, very illuminating.
Thank you. Yeah, thank you for the invitation and all the nice people meeting me. Yeah, it's really inspiring. Okay, thank you.
Thanks a lot.
Thanks.